Welcome to the AASHTOWare Pavement ME Design Fiscal Year 26 webinar number 3 on overview of output reports and data generated by AASHTOWare PMED. I'm Hari Nair, the chair of the Payment ME Task Force, and I'll be your moderator for today's presentation. Today's presenter will be Mr. Wouter Brink from Applied Research Associates. This presentation is being recorded and will be available on the ME Design resource website next week. Here are the Payment ME Task Force members. Ryan Fragapane, he is the AASHTOWare Product Director. Ben Said, AASHTOWare Associate Product Manager. And Ian Rish from Georgia DOT, who is the Vice Chair of the Payment ME Task Force. Nusrat Morshad from New Jersey DOT. Kumar Dave from Indiana DOT. Dixie Feldman from California DOT. Jason Simmons from Utah DOT. Robert Studler from Maryland DOT. And we have two liaisons, Diana Podboroshinsky, TAC liaison from Canada, and Tom Yu, Federal Highway. We encourage you to ask questions, and those will be addressed at the end of today's webinar. If you have questions, please click on the question and answer button to send your question to the host and panelist, and we will address this in the Q&A session directly after the presentation as time permits. Any questions not answered will be responded to separately. Now, Wouter will begin the presentations.
All right, so just to get going, some of the prerequisites for this webinar, just any prior experience with Payment ME Design. It could be either the desktop or web versions, and for anyone that's opened the output reports, which I think most probably have, the Word document, the Excel, or any of those. So the learning objectives for this webinar is to really just provide an overview of the outputs, identify the types of information that's generated by a Payment ME Design run that you'll see in the output reports, effectively review and navigate some of the different sections of the output reports, maybe show some maybe less known customizations that can be done based on new reports, and then also use some of the output results to help make design and planning decisions. As you see some of the time series plots, charts, and so on. So I'll go over most of those today. So for an outline, we'll start with a brief introduction and go over some of the items related to Payment ME Design and the overall mechanistic empirical design process. I'll do an overview of the data reports generated from the Payment ME Design analysis run. I'll also show two examples I'll open a new flexible and new JPCP example report and just kind of scroll through it. And then I'll summarize some of the items and then do a additional demonstration of the new structure builder that was released fairly recently, probably about a month ago, because I think most have not seen it yet, especially if you've not used the web app recently. Okay, to introduce, Payment ME has a lot of elements as inputs. So there's many different factors and items that are needed to complete a design run. So I mean, the main topics are, you have your site condition factors. This is where the climate inputs are, your traffic related items to a specific location, the different soils and foundation properties for where your design is located, and then also ways to characterize the existing pavement. So there's site condition factors, then you have your material properties. These include your volumetric properties, your mechanical properties, such as modulus and strength. You have your thermal properties and your performance-related properties tied to fundamental material laws. And then you have pavement design factors. You have your interlayer friction. You have your structural responses that get calculated internally. You have your damage indices, which then is also transferred through a transfer function to get your measured or your predicted distresses that you see at the surface of your pavement. So this includes your the transfer function from damage to, say, bottom of fatigue cracking, or transverse cracking in JPCP design. And then there's also the other design factors that are tied to your agency specific properties, such as your failure criteria. When does a distress exceed that predefined failure criteria? And then the outcomes from this is your pavement distress and reliability. So these are the main elements of the ME design process and the different broad categories of inputs that are needed and used throughout the analysis. And then how do those inputs and components feed into the final outcomes, right? So it's a systems approach where you have your climate, your traffic, your layer properties, and your design configurations. It feeds those inputs into a response model, which calculates whether, depending on the models, your stress, strains, and deflections. That data gets used within the transfer functions to define the fundamental material laws and damage. And then the damage is translated into your distress over time. So you'll have all of your distress prediction models and criteria. So you have, for flexible, main outcomes are your bottom-up fatigue cracking, top-down cracking, thermal transverse cracking, rutting, and your roughness in IRI. And on the JPCP side, or rigid side, you have your transfer slab cracking, and your roughness and faulting. And for CRCP, you'll have your punch outs and roughness IRI. So the question becomes like, how are all these results presented to you as a designer when an analysis is complete? And that's what I'll focus on here for the next couple slides. And so the summary of outcomes, the main goal of these reports are just to summarize your results. And that includes a detailed summary of the inputs that were used in the design and analysis. It includes calculated parameters such as mean values, aggregated on a monthly basis or even annual basis. You have your distress predictions that I just mentioned. And then we have some additional model generated data that is in the form of some intermediate files or just presented in one of the output reports. And then how are these displayed? There is a dedicated report that gets generated, which summarizes all of this. There's charts, there's tables, and different figures that provide the necessary information to show how your design performed over the design period that you have selected and used. So just to give a very brief overview again, what outputs are available with a design run. With the last version of probably the desktop app and the web application, there's three main categories of reports that are output. You have your XLSX, you have your docx, your Word file, your Excel file, and then a zip download, which includes a bunch of other files that you probably have never or wanted to look at. It includes many different items that I'll go over here in a minute. But these are your three primary outputs from the web app, and you can see a screenshot of how to download those once you have a completed design. So to dive into each one a little bit more, there's two categories of output reports. There's the primary results outputs, and then kind of a secondary result outputs. The primary outputs are what most are going to use for on a day-to-day basis. These include your Word file and your Excel file. Both reports contain primarily the same data. There might be some details in the Excel output report that might not be necessary or required in the docx, because you could just add a lot more detail of monthly values and so on in the Excel tabular form. So within each one, there's detailed summaries of all your inputs, which include your climate, traffic, and your layer and material properties. There's a detailed summary of all the outputs of your distress prediction results, your climate summaries, traffic summaries, material property charts, and so on. Then within the secondary results, this includes, let's say you might have heard some in the past about intermediate output files. This is files that are not necessarily intended to be used as the primary source of outputs. Most of the data from these files are already included in the other reports in some way. And it's really an artifact of the original MEPDG software after 137A was developed, and which relied on these files as an input and output for different modules. Most of these files aren't necessary anymore at all. They're just an artifact of what was available in the past, and no changes have been made to those. It's just the way it kind of worked out, where they're still available for those who do want to use or rely on them for some reason. And what is one benefit is some of these files can provide additional insights if interested. And I'll provide a couple examples of that further on in the presentation itself. So first, I want to do a detailed review and look at the different output reports. So I'll go over the different sections, and then I'll just do a demonstration and scroll through a individual output report and show the different components. So what I'll go over is the different headings. You have your design inputs, your design structure, design outputs and charts, which include your distress prediction summary and distress charts on the front page. Then you have detailed traffic inputs and charts, climate inputs and charts. You have your design properties and associated charts with those. You'll have also your analysis output charts, which add a few additional charts and figures to display some predicted results over time, whether it's distress or material values over time. I'll show some of those. Then you have your layer specific information and input summaries for as your asphalt, concrete, unbound materials, and so on. And then the last one is just a summary of your calibration coefficients and the transfer functions included. So I'll go into that right now. I'll open a new flexible design. And I should be back on audio. My headset turned off for a second, but it was a good transition there. I wasn't saying anything. Wanted to open the flexible report and go over the different sections. So first thing, you have your design inputs, just summarizes some of your design life, your design type, base construction, pavement construction, and traffic opening dates, the general information. It gives you a brief overview of your structure itself. So for this design, we have two asphalt layers, both 4 inches over a crushed gravel 6-inch base and a A6 subgrade. Provide some volumetric at construction information, which is just tied to the first layer in the structure, first asphalt layer. And then you have your heavy truck summary of your total number of singles, tandems, stridums, quads over the design period. So I created a very heavy traffic example here so that I can have some distress that shows up in the reports or the charts. And this one, basically over 20 years, it gives you a 20-year total heavy trucks. The next part is your distress prediction summary. This is what the most important probably of these reports. It shows you your target values, which is your distress threshold limits that you've defined in your design run, and each one for the different distress models. And then the actual predicted values associated for those models. And these values are at the specified reliability. So if you've specified 95%, that is going to be your 95% prediction value and associated to the blue line on all these charts. It provides you your target reliability and then what was actually achieved. And then also the final one is criterion satisfied. Did it pass or fail the specified limits? If it exceeds, fails. If it's below, it passes. Next part, your distress charts. So this is just a 4-figure summary. I know you can customize how these look or which ones show up in this first part. You're in the customized report section within the user interface, but primarily this just gives you a quick overview of how your design performed for these different distress models. So in this one, we can see IRI. We have our mean predicted values, always the black line, as you can see here in all of these charts. And then you have the added reliability based on your 95% or this one at 90% reliability level. So those are all the blue lines. So the way I interpret this, okay, well, IRI failed at about 17 years. Rutting passed, no issues with rutting, but it's quite a high threshold. So depending on the threshold level, it can fail. If you have a very strict threshold level where you don't want any rutting above, say, 0.25 inches, then this design would fail fairly early in its design period. Then for bottom-up cracking, we've got about, at reliability level, we have about 11 years of, it basically across about 10 years just to be safe. So we exceed the threshold of 25% bottom-up fatigue cracking at 10 years. And then for thermal cracking, it exceeds pretty early on. That's kind of just a general review of what this page is. I'll dive into some of these little examples a little bit more of how this can be used for some planning and design decisions. Next part of the report is your traffic inputs. Basically just summarizes what you've defined. If you have different axle distributions selected, it'll actually show which ones have been selected. If you use some of the predefined ones or your custom state-specific values, and charts of your ADT distribution by vehicle class. You can see your vehicle class distribution, your growth factors by individual vehicle class. These are just tied to how you enter the data in the inputs and your input screen. Your axles per truck by vehicle class, and then also just an adjustment factor, monthly adjustment factors if those have changed. I've used the default values here, so that's why most of these are kind of the same for everything. But many agencies have derived these values specific to their roadways and locations. Next part is just a tabular representation of the exact same data that I just showed on the previous graph. And then there's some axle configuration inputs that do impact your results, but typically are not adjusted unless you have specific data that supports different values. Next is your average annual daily truck traffic and growth over time. And the charts here specify your traffic over time for different vehicle classes. So you have vehicle classes 4 through 7 on one chart, classes 8 through 10 on the next, 11 through 13 on another, and then also all truck classes example. And then this is also aggregated into a cumulative heavy trucks. So this is all your heavy trucks combined into a single chart over your design period. And fairly recently, the cumulative easels were added. Internally, Pavement ME does not use easels. It uses the load spectra data directly, but easels can be calculated from that data with an assumed value for your load equivalency factors for rigid and flexible. So there's built-in defaults for those values, and this was a request quite a few years ago about just adding this as a reference, as additional information that can be used for comparison purposes in the design process. It is, if I want to reiterate, that it is not used in the actual analysis run. Next part just summarizes your climate data. So here we have our climate station. I use the one in Paxton, Illinois. It has the median annual air temperature calculations, your precipitation, your freezing index, and so on. Precipitation averages for every month. And then it has this kind of complicated graph of the hourly air temperature distribution by month. Especially for September, most of the temperature is going to be warmer, and then basically a heat diagram for this. Now, another useful section is the monthly climate summary. So as you selected a climate file, there's 30 or 40 years of hourly climate data, and then it summarizes that data into these charts. So you have your mean monthly air temperature, your maximum for that month, and your minimum. So you kind of see how your air temperature is distributed over your design period. Yeah, similar thing with your monthly precipitation, wind speed values, your monthly sunshine, which is really percent cloud cover way, and then your wet days. And then the last one in here is your monthly maximum frost depth. So the climate model within Pavement ME predicts frost depth and thaw depth over time. And this chart just kind of gives you your maximum value for each month. Now, where you can use this information is to see, okay, well, I know my frost depth is 40 inches, or predicted frost depth is 40 inches. Do I need to worry about frost penetrating my subgrade layers? So that's how you can use the information to adjust your base and subgrade or base layer thicknesses to prevent some frost reaching the underlying layers of your natural soil. So that's one benefit of these. You can, with the newer reports, you can change these, you can change scales, and so on. And I'll show you one of those in the next couple of sections. The HMA design properties is just your inner layer friction. Most of these are just presented, but some of the nice ones, nice data in here is your thermal cracking. So thermal cracking relies on your pre-compliance input data and your indirect tensile strength. So all that information's here. All of this is similar to the inputs you use for your top surface layer. And then you have the creep compliance master curve that is fitted to your data, input data. This was a more recent addition to the output reports to actually show you the fitted creep compliance master curve. This wasn't always available, and I don't think the desktop app has this available. And then you have the rest of your asphalt. You have your dynamic modulus master curve information, your shift curves, and your viscosity shift factors. And these are all presented for each asphalt layer that you have in your structure. And this data gets used in all of the flexible models themselves. Next part of the section is your analysis output charts. So this is basically reiterates the 4 charts in the beginning, but it has a little bit more granularity and you can see a few things a little bit better. The charts are bigger. They're not compressed as you kind of see in the first page, but same idea. IRI, total rut depth examples here. You have your bottom up cracking and then thermal cracking as well. Top down cracking. This is one of the distress that you did not see in the first page because you can only do 4 at this time. But this is an additional distress that you need to look at. It does show up in the summary report at the very top, what failed and what not. You have AC only rutting and some additional charts that are not, you can't see in other places. It's more of your AC top down crack depth. So the model predicts your depth over time. So you can kind of see where your layers are, what time is going to reflect through some of the
Wouter, I believe we lost you.
Sorry about that.
You're back now.
My mic keeps turning off for whatever reason. So you have your top down cracking, you have your bottom up damage predictions, you have your rutting permanent deformation on the individual layer basis. So you can see what the model predicts for your subtotal base, subgrade, and subtotal AC. And then some additional plots that are generated is your sublayer moduli for your asphalt materials. So if we look at here, this is your dynamic modulus over time for your specific design. And what's nice about here, you can actually zoom in a little bit. So if you change some of your limits here, let's look at the first 5 years. There's different sublayers of your moduli. It also says the mid quintile. The asphalt model actually does 5 different quintiles to kind of figure out where you're going to have the worst prediction based on the conditions. So it's basically you have low temperature, mid temperature, high temperatures for each month and different moduli values. And then I'll provide a little bit more of a overview of the sublayering in a couple minutes. You have your granular base sublayer moduli over time. So these are what gets used in your analysis when it goes into the structural response model. I changed some of the items here to switch between logarithmic and normal scale. You'll see these spikes of base layer moduli. That's about 1 million. That's typically representative of when you have a fully frozen subgrade or base material. And then you can see the equivalent here for your subgrade. Okay, well, I know that at one point there's maybe partially frozen or fully frozen items, or times throughout the design period where your subgrade might be subject to frost. So these are nice outputs to help you make decisions and see what is available, and just help you plan for future items throughout your design and make decisions of changes and getting an optimized design. I'm not going to go into too much detail about the inputs, but they are all summarized here for every one, for every layer. And then the last part is your transfer function and equations and calibration coefficients associated with that design. So that's it for the new flexible. I'm going to quickly go through a JPCP report, but as you'll see, I mean, most of the stuff is the same. IRI faulting, JPCP transfers cracking, so all those are shown. Traffic is nearly identical, except this has hourly distribution because that matters between top down, bottom up transfers cracking. Then we have, I'll just scroll towards the bottom. The only additional charts here are your PCC moduli, your flexural strength, and your base modulus, and your subgrade dynamic K value. So I know I'm going through these pretty quickly, but I mean, they're mostly the same as the flexible, except what the PCC design modules use. And then you have your cumulative damage. The blue line here is your top-down damage, which is mostly nighttime when the slab curls, depending on the daytime temperatures and nighttime temperatures. So either curls up or down. And then you have also your bottom up. Another item unique to the JPCP is your load transfer efficiency. As you see, these items help with kind of see how your dowels are performing. It's typically not an issue when you have dowels. Your load transfer efficiency is going to be quite high, and this directly impacts the amount of faulting that the model predicts. And then it's just the layer inputs like we saw for flexible. So it's a pretty quick overview of some of the rigid or JPCP items. Now I want to get into some of the other. I'm going to skip through quite a few slides here because it's just backups. Now the other section I want to go over is the intermediate output files. So just as a reminder, they're not intended to be used as a primary source of outputs, as they're artifacts of the original MEPDG, but there is value in these where if you want, you can dive into them and provide some additional insights. They can provide some additional insights if that is something that you are interested in. Some examples of these files that you'll see in here, there's your pavement temperature with depth for the bound layers, so your asphalt temperatures on an hourly basis. How do those what does that look like? Your temperature gradients throughout your structure for flexible and rigid. You have fatigue damage. You have your bottom up or you have a JPCP cracking and faulting files. You have your dynamic modulus master curve outputs. You have other EICM related temperature data, your thermal moisture index calculations, the traffic calculations, and so on. Some are more beneficial than others, but I'll go through one that is might be of interest to some. And that one is the fatigue damage file. It's a .fat format. This file really summarizes the total fatigue damage at different depths and analysis locations from the analysis module within the flexible design, where the total fatigue damage is a function of your load repetitions, your monthly load repetitions over your total allowable load repetitions. So it's the N over N, your damage function. The maximum value on a monthly basis from these is used to predict your bottom up fatigue cracking. And then the damage values represent the sum of all your actual types in single tandems, trinems, quads. Just to give some background information, when an analysis runs for flexible design, we have a tire, basically a structure here. We really just we're looking at your axle configuration. This is a single axle with dual tires. The origin runs through the center of those two tires. We analyze one half of that, and because we know the other half is the same, And then tandems, tridems, and quads are analyzed through superposition based on this single tire location in analysis structural response run. Analysis locations, there's 10 different locations that are always included in an analysis run. The actual values depend on some of the tire configurations, your axle configurations, your spacing between your dual tires, and so on. So those X locations are predefined. I mean, they're not directly adjustable. They are dependent on some inputs. The Y locations are dependent on your axle type, so singles, tandems, tridems, and quads, and those spacing values. And then the responses are calculated at the single location along the Y-axis, and then the responses at other locations are determined through superposition. And by default, it uses standard wheel load 4,500 per tire, and then some of the tire pressure and so on. Why I wanted to provide this is that it really sets up the problem that sets up the solution for how these files are and fatigue data is presented. So within this .fat file, there's a text file with data. So there's a bunch of different lines. You have the first part is your number of sublayers and the sublayer depths. Then the next part is your number of analysis locations that I showed previously, where you have analysis location in your X direction. And then the items down here is your number of months. So it's a 240-month design. And then you have your fatigue damage data corresponding to different depths and analysis locations. And to brief overview of at least the sublayering, your structure itself has layers, and then you have sublayers. And the layers themselves are divided into sublayers based on what the 137A came up with for the flexible analysis. So you have this particular structure. One of these structures you have two asphalt layers and a base layer and a subgrade. So the asphalt layers, you have a 4-inch surface layer and a 4-inch leveling or base layer. Now the asphalt is subdivided into multiple sublayers for the 0. Based on different depths throughout. So first one is 0.5 inches, 0.5 inches, and then it's basically 1-inch increments until the depth of 4 inches, and then 4 inches until 8 inches is basically into a single sublayer. And that's where you can kind of see in this previous one where we have 1/2 inch, 1 inch, 2 inch, 3 inch, 4 inch, 8 inch. So those are the different sublayers for the structural analysis portion. And then there's logic for the unbound layers themselves. Now I went ahead and used that data, adjusted the file, copied the data into Excel, added assigned the depths and analysis locations to each damage value, and then plotted the results for your structural response or your total damage as a function of your analysis location. So what you can see here is this at least
Hey, we may have lost you again, Wouter.
Yep. Yeah, sorry about that. I don't know why it keeps timing out, but I'm just prepared it might happen again. I think it's on a timer. But anyways, so we can see here with the different lines or different sublayer depths. So I have your surface layer, which is this first one. This is not going to be your critical response. So you have 1 inch, 2 inch, 3 inch, 4 inch, 8 inch, and 10 inch in this example. It's not the same example as the previous screen, but as you can see, I looked at the last month at 240 months. Your maximum damage occurs in your 10-inch at the 10-inch depth, so it's basically at the bottom of your asphalt layer, and the maximum distress really happens right at the origin, which is between the two wheel loads. So that's how it ended up for this design, but it can help at least give an idea of where the critical damage is located. It doesn't give you direct stresses and strains, but it gives you the total damage combined. Now we are doing a rework of the the task force agreed to rework of the structural response outputs. So that's coming next year. So we're working on that to provide some useful outputs for the structural responses themselves. Now, another example of how this data can be used, I ran an example with full friction versus no friction between the different layers. So basically the one on the left here, there's a full bond between the two asphalt layers and the unbound base. And then on the one on the right here, I set that value to no friction between to see how the model reacts and how the damage is different. So as you can see with the full bond, the critical locations are closer to or right at the bottom of the asphalt layer, so at the bottom of your 8-inch total structure. And then on the right here, because there's no bond between these two layers, now you can see that, okay, well, that's ends up being your critical response location. So if you have weaker layers, it's not always going to be that the critical response is going to be at the bottom, depending on how you define that the condition of that friction or friction or bond between the two different layers. This is just to illustrate some of the differences between these files and then how you can actually how it does impact your outputs, and you can see some differences there. So as you can see, I just put here from max location. They are different between the two because there's no bond between the two asphalt layers. Some additional examples that I put together here. So for JPCP faulting.csv, it's an intermediate output. It has your LTE components, your joint opening, loading, unloading, deflections for singles and tandem axles, your differential energy, and your dowel damage. All that is on a monthly basis. So you could actually do some plotting there if you want to see which components impact your predicted faulting the most. So here's an example of your load transfer efficiency. So you have the PCC LTE, which is really the combined effect of your concrete and aggregate interlock within your concrete structure. You have your dowel specific LTE, and then the total. And then the differential energy. This impacts the faulting predictions over time. Also predicts your joint opening and then dowel damage. Just an example for your JPCP cracking. Bottom-up damage by axle type and top-down damage if you want to look at the different components. As you can see, they can be plotted next to each other. These are not an output by default. You have to, I did these by myself. I mean, you can open the CSV, just create the charts with it. There's quite a bit of good information there. You can also see your PCC strength gain over time and so on. So another example to use some of this information is you can use the distress predictions and year when the thresholds are exceeded to help identify potential future maintenance or rehabilitation activities. So as we all know, all pavements will require maintenance and or rehab eventually. You can use the agency defined thresholds in conjunction with your maintenance schedules criteria if you know you need to do something to that pavement at some point, even if that's based on your condition or current condition, or if you're doing it on a specific standard schedule of, say, every 10 years, 15 years, 20 years, you do something. One way to look at that is you can string together multiple designs in a way where you have your new design, you use the outputs from that new design, predicted outputs to define the existing condition of your overlay design. So that's one of the most critical things in overlay design is how do you characterize and what's the condition of that existing roadway. So I think the first thing here is, so say we have our distresses here, we can use the information from these predictions to define, say, the existing condition of an overlay. If you want to do a kind of the chained approach, if you're doing it for the entire life cycle of that asset or structure or pavement location, you have your fatigue cracking, rut depth, thermal transverse cracking are all inputs needed in the overlay module. So you can use your predicted results and age when those thresholds are exceeded as a guideline. And then you can use this for long-term planning purposes if needed. Just an example. So once we have, this is a new design, we know, okay, well, it's going to crack. Well, it's going to exceed the threshold at about 11 years. What's the distress bottom of fatigue cracking at that time? So you can see, okay, well, that is an input in the rehabilitation design. And then also say if we have thermal cracking, that also goes into this point here. The rehab modules also require your layer rut depths, and Pavement ME predicts asphalt rutting, subgrade rutting, and base rutting. So those do impact your future overlay designs, and so it really matters, especially to define the strain state at that time of when you're doing an overlay. So in summary, this is a lot of information. AASHTOWare has many inputs and many outputs. Primary outputs include the docx, your XLSX reports. Your secondary outputs include some of the immediate output files in the output folder. And then output documents can be used to really analyze results beyond what's currently there. If you want, create additional charts or figures, and assist with some decision making during the design phase to provide additional insights. So that's it for the data items. I want to now go quickly do a demonstration of the new structure builder that was recently released. So the remainder of the webinar will be some of that, and I'll go into that. Okay. So as many of you know, here's our main page. I didn't change. I'm already logged in here, but what I'm going to do is go ahead and create a new design. I'll just call it webinar demo and create it. So now we created it. I'll open the item itself. Let me zoom in a little bit so everybody can see. So the first thing you'll notice, there's been a rearrange of the different components within your menu here. You'll see general information. This used to have a bunch of other items. Now it's just your design name, your design life, and what units you want to use. Next in line is traffic, your climate, and then structure. And then you might notice, oh, well, there's a bunch of things missing. And that's by intent, because once we define our structure, traffic, you can input there, climate, I'll just select a random location here, close to where I'm at, just to get the red exclamation point out of the way. And there we go. And now we go into the structure builder. So this is probably the biggest change you'll see. So instead of you selecting a dropdown of new, overlay, recycle, all these different templates that were basically templates built into the system, now you can basically you build your structure from scratch or use a predefined template by itself. So we have on the right here is your library, and it's separated by templates and materials. So the first one is templates. These are complete designs, or at least designs that will be able to run. So these are similar to when you created a new flexible design in the old structure definition. Now it's just defined here. You have new, you can separate by new, first overlay, multiple overlay, or recycling strategies. And those are all in here. So there's two ways you do this. Click on your apply template. It's going to pop up a warning that everything will be removed, all the surface layers, and then you click apply. Now you have a structure. And by default, based on this structure, the software is going to tell you that this is the only valid design strategy for this exact structure is a new flexible design. Okay, well, maybe I want something else in there. Okay, now we can customize these no matter what. So once we customize and add different layers, we can go to
Oh, gotta reset your audio.
back, hopefully. All right, I'm back. So now we have our different materials. And say we want to add another asphalt layer. We have our different materials here selected, asphalt. We have our default materials that come with the software, as well as if you have any predefined material libraries that you've created, those should also show up in here automatically. You can easily search to, say if you want cold in place or asphalt, if I can spell. Where is that one? well, it didn't go. So I'm just going to put in a default asphalt layer in here. Same thing. We still drag and drop. Now it shows me, okay, well, it's only valid for a new flexible. Okay, well, let's put a construction separator in here. So this is how you define or characterize if it's a new or an overlay, or where do you define your existing structure. So if that second layer is in an existing and I want to put an overlay, I drag and drop this in here. Okay, well, now I know that I have an overlay layer, an existing flexible, and then my underlying layers. But now you'll notice that the selected design strategy is blank. Okay, well, what does that mean? That means that there's multiple options available for your current structure. So once you click on that drop down, now we'll see we have AC over AC, AC over AC with seal coat, AC over AC with an inner layer. So then you have to select which design strategy you want, and then the rest will kind of fall in place for the materials, your design properties, performance criteria, and so on. There are some additional guidance here with the analysis path requirements. This kind of gives you, if you want to build an AC over semi-rigid design, this one, okay, well, you have to have one chemically stabilized layer. Okay, so if we want that particular design, we can go to our cement base, add a cement stabilized layer, and now this particular structure is an AC over semi-rigid. And there's no other design strategy or analysis path that can be defined for this particular structure. One other example, say if we want to start from scratch here, I want to show okay, let's put in a PCC layer. I want non-stabilized base, just put an A1A, and then a subgrade. Oh, so that didn't go in there. Okay, so now you see, okay, we have a PCC layer, non-stabilized base, and subgrade. So what we haven't defined if it's a JPCP, CRCP, or what is it? And that's where this is kind of nice, where you just put in the layers that you have, and the software will tell you what available design strategies are available. So now I'm going to just new JPCP, the rest gets filled in, and so on. So that's kind of a very quick overview of the structure build itself. It's a change compared to how it used to be, but I think it'll lessen some of the confusion and use cases where you have the recycling layers for your full depth reclaim, full depth reclamations, your cold in place recycling, all these different strategies that were added as part of the multiple overlay and recycling strategies a couple of years ago. The rest remains the same. It's just a different way to build your structure and let the software kind of tell you what appropriate design analysis paths are allowed for the structure that you have built. The rest is, like I said, identical. Your PC, once you get in the materials, you can still change there. If you want to edit your structure or the thicknesses, you just click on edit. It automatically takes you back to your structure builder section. And yeah, I mean, that's really it for the structure builder itself. And I'll go back to the presentation. I have some placeholders here for the templates and drag and drop.
Okay. In the interest of time, and to do a little bit of Q&A, I'm going to end this poll now. And Hari will lead us through some Q&A. There's a couple of open questions.
Most of the questions are already answered by John and Sri. Only a couple of questions left. Wouter, one question is thickness optimization more efficient now, especially for flexible pavements?
I mean, there's always model changes going on to improve efficiency, but it's hard to. We haven't had any issues with it. The thing with thickness optimization is it runs the low end, the high end, and anything in between until it gets a passing design. So depending on what values you enter and the levels between them, it's going to create a run for every single combination. But I mean, we haven't had any issues with runtime, I don't think. So, I mean, it's more efficient than the desktop app, certainly, just with how the web app is structured and built. So it should be more efficient, but it just depends on how many increments you're trying to do. So I mean, this still has to run the ICM, it still has to run
Correct.
APAS and Julia and all the models.
Well, another question is, could you please clarify how PMED defines the three roadway categories, interstate, primary, and secondary? Do these categories map directly to FHWA functional classes? And if so, which specific roadway functional classes fall under primary and secondary?
I mean, I don't have a great answer for that because the manual of practice kind of defines some of those, but I don't know what the exact criteria is for interstate, primary, or secondary. I mean,
So it is in the manual of practice, correct?
there's some defaults that are defined in the manual of practice tied to interstate, primary, or secondary. Yeah, but I
Okay.
don't know if it directly maps the FSWA items. I just don't know.
Okay. I think another question is, if a design structure template is developed under library, is it possible to cross-link the calibration library with that customized template? I think
Yeah,
that's possible. It should be
yeah,
possible.
yeah, it should be possible. And if it's not there, send us a note. I know there's continual work on the calibrate the libraries themselves and the interaction. I know there's been a couple of requests on that, and I know there's features coming for being able to apply and revert to default calibration sections and so on. If it's not there yet, I mean that'd be a great feature to add. But I'm pretty sure it's tied to if you build a structure template with those coefficients, they should all be applied.
Yeah. I think this question was, I think John answered this question, but they're asking what will be the workaround if we are getting different results from the desktop and web-based version? I think they found that they are getting different answers when they use web-based version versus
Yeah.
the desktop version.
So I mean that kind of depends on the calibration files or the models that you're using. Like there should not be a large difference between version 2.6 desktop app and the web app for flexible payments because none of the calibration coefficients changed. There's been bug fixes, of course, but none that should have impacted calibration. Now, on a rigid side, the desktop app was last calibrated in 2016, maybe even before that. And for the web app, there's a very different model. The HHRP 1-51 results have been integrated. So you are going to see differences between the desktop app and web app. But that's why it's so important that you need to verify that you can move. Now for flexible, it should be okay to move from 2.6 to version 2. Or version 3.0. But for rigid, you have to really look at there are going to be significant differences, and those have been outlined in previous webinars, especially when the web app was released. The desktop app will be sunset in a couple of years, so everyone's gonna have to move to the web app at some point.
So another question is, how are the predicted and the achieved values calculated for each of the distresses in the prediction summary? Are the equations for these values located in the report anywhere?
Trying to figure out where.
Predicted and achieved values calculated for each of the distresses.
Oh, so you're talking about I see what you're, yeah. So basically in the output report up here, if you have a predicted value, which is just the exact value at 20 years or at the end of your design life, 121. In this case, it's all tied to the reliability and the target value and what you have achieved. So this one's 100% is achieved. So basically your reliability level from 120 compared to your threshold, it's 100%. And the same here is like, okay, well, the 95% value is greater than the 90, but it's all kind of tied to what your threshold value is and your slabs and your final predicted value. So if you look at the flexible report, you'll see here that some fail. It's just a reverse calculation of what's your actually achieved reliability percent compared to your threshold limits. It's a good question. I don't think it's very clear how to interpret that data to most folks. So, I mean, that's something that we can take down as a note for a future explanation in the help manual or somewhere else.
Hey, Wouter, can I quickly answer that?
Sure.
Yeah, and that comes from the standard deviation. So if you look at go back to the previous file that you had, I think the PCC one, yeah. So if you look at the first one, like the terminal IRI, you can see how the predicted is so far from the target, and that's why you see that it's 100%. So it's like multiple standard deviations away from the target. But if you look at the faulting, you can see the zero point 0.1, it's passed, but it's close to the target of 0.12. And so it's only two standard deviations away. And there's a standard deviation formula that's shown later in the report, and it uses that to calculate. So it's basically some statistical analysis between the mean and the standard deviation that's used to calculate the reliability.
Thanks, Sri.
Wouter, the last question is how one can decide the threshold values other than provided in the manual of practice?
I mean, that's really an agency specific decision based on how they design their roadways. So, I mean, when do they continually perform re-up designs or go and do something to that pavement? That's really what it needs to be tied to. What level of performance and at time when you're going to do something to that roadway. I mean, that's really what the manual practice just has generic values that can be applied, but I mean, that's up to you and the agency to define those threshold values. So it's hard to give you a specific number or criteria, but the manual practice should actually provide like that these need to be agency specific and defined based on what you're seeing on your roadways and how they perform.
Thank you, Wouter. When we are done with all the questions.
Yep. I'm hopefully we answered everyone's questions. Thank you so much for attending this AASHTOWare webinar. This webinar was recorded, and that'll be available along with all past webinars on our YouTube channel, which is at AASHTOWare Pavement ME Design on YouTube. There's a QR code to the YouTube channel right here. Lots of excellent content as well, including some short training videos on specific pieces of the software. So head over to YouTube and check out some of those additional trainings. In addition, for more in-depth training on the concepts behind the software, there is a course on mechanistic empirical pavement design at store.transportation.org, and that is under MEPDG for those looking for a more in-depth course on the fundamentals of the principles behind the software and the AASHTO standard. So feel free to go check that out. That is free for state DOT members and for a small fee for contractors. With that, thank you so much to our presenter, Dr. Wouter Brink, and our moderator, Hari Nair, and our other panelists, Sri Rao. We'll see you next time. Thank you so much.
Thanks, everyone.